let me tell you something that might change the way you think about numbers. Not in a big dramatic way, but in that quiet way where something shifts in the back of your mind and you realize you'd been carrying around a slightly wrong picture of things for years without knowing it. That's what mathematics does, actually. It sneaks up on you, and tonight, we're going to let it. So settle in. Get comfortable. We're going to wander through some of the most confusing, most misunderstood, and honestly, most beautiful ideas in all of mathematics, and we're going to do it slowly. There's no test at the end. There's nowhere you need to be. If you drift off somewhere between imaginary numbers and infinity, that's perfectly fine. The ideas will still be here. And honestly, some of them make more sense when you're half asleep anyway, because your waking brain tries too hard to force them into boxes they don't quite fit in. Let's start at the very beginning, and I mean the real beginning, not with algebra or calculus or any of the things that might have given you trouble in school. Let's start with counting. Because here's the thing, counting is stranger than you think. Imagine you're standing in a field about 6,000 years ago, somewhere in ancient Mesopotamia, in what's now southern Iraq. You've got a flock of sheep, maybe 30 of them, and your problem is simple. You need to know if all your sheep come back at the end of the day. That's it. That's the whole problem. But you don't have numbers yet. The concept of 30 doesn't exist in your mind as an abstract thing. So what do? Well, what people actually did, and we know this from archaeological evidence, is they used tokens. Small clay tokens, each one representing one sheep. You keep the tokens in a pouch or a clay container. Sheep goes out in the morning. You move a token to one side. Sheep comes back in the evening. You move it back. If you've got tokens left over at the end of the day, you're missing sheep. It's a one-to-one correspondence. Each token maps to exactly one animal. And that right there, that simple matching, this thing goes with that thing, is the deepest foundation of all mathematics. Before you can count, before you can add, before you can do anything at all with numbers, you need this idea that two collections of things can be compared by pairing them up. Now, you might think, okay, that's obvious. Of course you can match things up. But think about what's really happening here. The shepherd doesn't need to know the number 30, doesn't need a word for it, doesn't need a symbol for it. All they need is the correspondence itself. The tokens and the sheep are in a relationship, and that relationship tells them everything they need to know. This is going to come back later tonight when we talk about infinity, and it's going to get genuinely weird, but for now, just hold on to that idea. Mathematics, at its root, is about relationships between things, not the things themselves. The relationships. So these Mesopotamian people, the Sumerians, and later the Babylonians, they started with tokens. And then, around 3,200 BCE or so, something remarkable happened. They started pressing the tokens into wet clay tablets before sealing them inside clay envelopes. So now you've got the imprint of the token on the outside and the actual token on the inside. And pretty soon somebody realized, well, if you've got the imprint, you don't really need the token inside anymore, do you? The impression in the clay is enough. And just like that, you've invented writing, or at least one form of it. Some historians argue that mathematical record-keeping was actually one of the driving forces behind the development of written language itself. Numbers might have come before words. Think about that for a second. Before we wrote down stories or laws or poetry, we might have been writing down how many jars of grain were in the storehouse. The Babylonians ended up developing something really interesting, a number system based on 60. We use base 10, probably because we have 10 fingers. But the Babylonians used base 60, which is called sexagesimal if you want the fancy word. And you're still using their system every single day. Every time you look at a clock and see 60 seconds in a minute and 60 minutes in an hour, that's Babylonian mathematics reaching across 4,000 years to tap you on the shoulder. Every time you measure an angle, and there are 360 degrees in a circle, that's base 60 again. 6 times 60. The Babylonians are everywhere, hiding in plain sight. And here's what's really clever about base 60. 60 is divisible by a lot of numbers. You can divide it evenly by 2, 3, 4, 5, 6, 10, 12, 15, 20, and 30. Compare that to 10, which you can only divide evenly by 1, 2, 5, and 10. This matters because when you're doing practical calculations, splitting up grain, dividing land, figuring out trade, you want to avoid fractions as much as possible. Fractions are messy. They were messy 4,000 years ago, and honestly, they're still kind of messy today. So using a base with lots of divisors means you run into fewer fractions in everyday life. It was a pragmatic choice, and a surprisingly sophisticated one. Now, the Babylonians had another trick up their sleeve, and this one is going to lead us into our first genuinely confusing mathematical idea. They used a positional number system. That means the value of a symbol depends on where it appears. We do the same thing. When you write 352, the 3 doesn't just mean 3. It means 300s because of its position. The 5 means 5 tens. The 2 means 2 ones. Position determines value. The Babylonians did the same thing, but in base 60, and this is a huge deal. Most ancient civilizations didn't do this. The Egyptians, the Romans, their systems weren't positional. In Roman numerals, X means 10 no matter where you put it. That makes the system simpler in some ways, but much harder to actually calculate with. Try multiplying 47 by 29 using Roman numerals. It's a nightmare. The positional system makes arithmetic dramatically easier, and the Babylonians figured this out thousands of years before it became standard everywhere else. But here's the problem they ran into, and it's a problem so fundamental that it took humanity a couple thousand years to fully solve. What do you do when you have nothing? I mean that literally. If you're writing a number in a positional system and one of the positions is empty, say you want to write the number we'd call 302, where there are no tens. How do you indicate that? The Babylonians eventually started using a small symbol, a pair of angled wedges, as a placeholder to show an empty position. But they didn't think of this placeholder as a number. It wasn't 0 in the way we understand 0. It was more like a punctuation mark. It said, nothing goes here, without actually being a quantity called nothing. And this is where things get philosophically interesting, because 0 is genuinely one of the most confusing ideas in the history of mathematics. Not because it's complicated to use, you use it all the time without thinking, but because of what it represents. What is nothing? Can nothing be something? If you have 0 sheep, do you have sheep? It sounds like a silly question, but it tripped up some of the greatest minds in history. The ancient Greeks, who were brilliant mathematicians in so many ways, were deeply uncomfortable with the idea of 0. For the Greeks, numbers were tied to geometry. A number represented a length, or an area, or a ratio. What's a length of 0? It's no length at all. It's the absence of the thing you're trying to measure. Many Greek philosophers argued that 0 simply couldn't exist as a number, because a number, by definition, had to represent some quantity. The people who really cracked 0 open were Indian mathematicians, And this is a part of the story that doesn't get told nearly enough. Around the 5th century CE, and probably earlier, Indian mathematicians began treating 0 not just as a placeholder, but as a full number in its own right, a number you could use in calculations. Brahmagupta, working in the 7th century in Rajasthan, wrote down explicit rules for arithmetic with 0. 0 plus a number is that number. A number minus itself is 0. 0 times anything is 0. He even tried to tackle division by 0, which, well, we'll get to that. But the point is, Brahmagupta treated 0 as a legitimate mathematical object, and that was revolutionary. It changed everything. Without 0 as a real number, you can't have algebra as we know it. You can't have calculus. You can't have the coordinate system, where 0 is the center point. You can't have negative numbers, really, because negative numbers only make sense if there's a 0 for them to be on the other side of. And speaking of negative numbers, let's talk about those for a moment, because they confused people for an astonishingly long time. Think about what a negative number means. You're saying there's a quantity that's less than nothing. If I have -3 apples, what does that even mean? I can't show you -3 apples. I can't put them on a table. It's a pure abstraction, a number that represents owing or lacking, or going in the opposite direction. And for centuries, mathematicians called these numbers absurd, fictitious, false. Even in the 1700s, some European mathematicians were deeply suspicious of negative numbers. Francis Maceras, an English mathematician, wrote in 1758 that negative numbers darken the very whole doctrines of the equations and make dark of the things which are in their nature excessively obvious and simple. But here's the thing, negative numbers work. They're incredibly useful. As soon as you want to describe debt, or temperature below freezing, or elevation below sea level, or the direction of a force, you need negative numbers. And Indian and Chinese mathematicians had been using them comfortably for centuries before Europeans came around. Chinese mathematicians were using red and black counting rods to represent positive and negative numbers as early as 200 BCE. Red rods were positive, black rods were negative. They didn't agonize over whether negative numbers were real. They just used them, because they worked. And this is something you'll see over and over again in the history of mathematics. A new idea appears, and it seems wrong, or impossible, or absurd. People resist it, sometimes for decades, sometimes for centuries, and then eventually, the idea proves so useful, so powerful, so good at describing the world, that resistance just melts away. The idea gets absorbed into the mainstream, and the next generation of students learns it as if it were obvious, never knowing how much struggle went into accepting it. That pattern, confusion, resistance, acceptance, and then, well, obviously, it plays out again and again. It happened with 0. It happened with negative numbers. And it's about to happen with something even stranger. Because once you've accepted negative numbers, there's a natural question that comes up. And it's a question that leads to one of the most beautifully named objects in all of mathematics. If you can have a number whose square is positive, 3 times 3 is 9, -3 times -3 is also 9, then can you have a number whose square is negative? What number, multiplied by itself, gives you -1? Think about that. Any positive number times itself is positive. Any negative number times itself is also positive. So nothing on the number line, nothing you've ever encountered, can give you a negative result when you square it. And yet, mathematicians started running into equations where you needed exactly that. You needed the square root of -1. And for a long time, they just called it impossible. Girolamo Cardano, the Italian mathematician working in the 1540s, encountered these strange square roots of negative numbers while solving cubic equations, and he called them as subtle as they are useless. He could see that they appeared in his calculations, but he didn't trust them. He used them reluctantly, almost holding them at arm's length, the way you might pick up something you're not sure is clean. But then, something started to happen. Other mathematicians noticed that if you just held your nose and worked with these impossible numbers, if you pretended they were real and followed the rules of algebra, you got correct answers. Real, verifiable, useful answers. The impossible numbers appeared in the middle of a calculation and then canceled out at the end, leaving you with a perfectly normal result. They were like scaffolding. You needed them to build the building, but once the building was done, the scaffolding came down and everything looked solid. Raphael Bombelli, another Italian mathematician, was one of the first to take these numbers seriously, working out careful rules for how to add and multiply them. And slowly, grudgingly, the mathematical world began to accept that maybe these numbers weren't impossible after all. Maybe they were just a different kind of real, a kind of real that we hadn't made room for yet. And that's exactly what happened. The name they eventually got, imaginary numbers, is honestly one of the worst names in all of mathematics. It was meant as an insult. René Descartes, the French philosopher and mathematician, coined the term imaginary in 1637, and he didn't mean it as a compliment. He was basically saying these numbers were made up, fictional, not to be taken seriously, and the name stuck, which is a shame, because there is nothing imaginary about imaginary numbers. They're as real as any other number. They show up in electrical engineering, in quantum mechanics, in signal processing, in fluid dynamics. Every time you use a cell phone, imaginary numbers are doing work behind the scenes. But for a couple of centuries, the name kept people suspicious. It's hard to trust something called imaginary. So let's talk about what actually happened, because the story of how imaginary numbers went from being a mathematical embarrassment to being one of the most powerful tools in all of science. That story is worth spending some time on. The key figure here is a self-taught Swiss bookkeeper's son named Leonhard Euler. Euler, born in 1707 in Basel, Switzerland, is one of those people who makes you question whether the rest of us are even trying. He published more mathematical papers than any human being in history, over 800 of them, and he kept working even after he went blind in his later years, dictating papers from memory. The man was a force of nature, and one of the many, many things Euler did was give imaginary numbers a proper notation. He's the one who said, let's just call the square root of -1 I. Just the letter I. Simple, clean, no fuss. And once you have I, you can build a whole number system around it. Any imaginary number is just some real number multiplied by I. So 3I, -7I, half of I. These are all imaginary numbers. And when you combine a real number with an imaginary number, like 4 plus 3I, you get what's called a complex number. Complex, not because it's complicated, but because it's a composite. It has two components. Now here's where things get really beautiful, and I want you to picture this in your mind. You know the number line, right? That straight line stretching from -infinity on the left to +infinity on the right, with 0 in the middle. Every real number lives somewhere on that line, but imaginary numbers don't fit on that line. There's no place to put them. So what do? You add a second line, You draw it perpendicular to the first one, going straight up and down, and you put the imaginary numbers on that vertical axis. Now you've got a flat plane, a two-dimensional surface, where every point represents a complex number. The horizontal position tells you the real part. The vertical position tells you the imaginary part. This is called the complex plane, and it was developed in the early 1800s by a few different mathematicians. But the one who really nailed the geometric interpretation was a quiet, unassuming Norwegian-Danish surveyor named Caspar Wessel, who published a paper about it in 1799 that almost nobody read. A few years later, the Swiss mathematician Jean-Robert Argand independently came up with the same idea, and eventually the great Carl Friedrich Gauss, who we'll talk about more in a bit, helped cement it as standard mathematical thinking. But here's the thing that matters. Once you can see complex numbers as points on a plane, multiplication suddenly has a geometric meaning. When you multiply two complex numbers, you're not just doing arithmetic, you're rotating and stretching. Multiplying by I is the same as rotating 90 degrees counterclockwise. Do it twice, multiply by I squared, and you've rotated 180 degrees, which is the same as flipping to the negative side of the number line. And that's why I squared equals -1. It's not some arbitrary rule. It's a rotation. 2 quarter turns make a half turn, and a half turn takes you from positive to negative. When you see it that way, imaginary numbers stop being mysterious. They're just a way of talking about rotation and direction in 2 dimensions. And this is why electrical engineers love them. Alternating current, the electricity flowing through the wires in your walls right now, is a wave that oscillates back and forth, and describing that oscillation mathematically is so much easier with complex numbers than without them. The voltage and current aren't just magnitudes, they have phase, which is basically a way of saying where they are in their cycle of oscillation at any given moment. Complex numbers capture both magnitude and phase in a single elegant package. So when an electrical engineer writes down a complex number, they're not doing abstract philosophy. They're describing something as concrete as the power keeping your lights on. All right? So we've gone from people being terrified of 0, to people being suspicious of negative numbers, to people being outright hostile toward imaginary numbers. And in every single case, the pattern is the same. The new numbers seem impossible or absurd at first. Then people discover they're useful. Then people discover they're actually essential. And eventually they become so normal that nobody even thinks about them anymore. You use negative numbers every day without a second thought. You check the temperature and it's -5 degrees and you don't have an existential crisis about it. Someday, maybe already, imaginary numbers will feel just as natural. But let's shift gears a little. Let's talk about something that trips people up in a completely different way, and it's one of the most fundamental things in all of mathematics. Let's talk about infinity. Now, I mentioned earlier, way back when we were talking about Sumerian shepherds and their clay tokens, that the basic idea behind counting is one-to-one correspondence. You match each sheep to a token. If the tokens and the sheep pair up perfectly with none left over, you have the same number of each. You don't even need to know what that number is. The matching is enough. This idea is so simple that it seems almost trivial. But it turns out to be one of the most powerful ideas in the history of mathematics, because it's the key to understanding infinity. And the person who unlocked that door was Georg Cantor. Cantor was a German mathematician born in St. Petersburg, Russia, in 1845, and his story is one of the most dramatic and heartbreaking in all of mathematics. He spent his career at the University of Halle, which was not exactly a prestigious institution. He wanted a position at the University of Berlin, the center of the mathematical world at the time. But he never got one. And the reason he never got one is largely because of the work he did on infinity, work that made him famous and also made him enemies. Here's the question Cantor asked. It sounds simple. Are there different sizes of infinity? Think about that for a second. You know that the counting numbers, 1, 2, 3, 4, 5, and so on, go on forever. There's no biggest number. That's one infinity. But what about the even numbers? 2, 4, 6, 8, 10. There are obviously fewer even numbers than counting numbers, right? You've thrown away half of them. So the infinity of even numbers should be smaller than the infinity of all counting numbers. Makes sense, right? Except it's wrong. And here's how Cantor proved it. Go back to one-to-one correspondence. Can you match every counting number to an even number with nothing left over? Sure you can. Match 1 to 2. Match 2 to 4. Match 3 to 6. Match 4 to 8. Every counting number n gets matched to the even number 2n. Every counting number has a partner, and every even number has a partner. Nothing's left out on either side. The matching is perfect. And if two sets can be put into perfect one-to-one correspondence, then by definition, they're the same size. So there are exactly as many even numbers as counting numbers, even though one set is contained inside the other. This is the first sign that infinity doesn't behave like ordinary numbers. With finite sets, if one is a proper subset of the other, if it's entirely contained within the other with room to spare, then it's definitely smaller. But with infinite sets, that logic breaks down completely. An infinite set can be the same size as a part of itself. That's actually one way to define what infinite means. And Cantor didn't stop there. He showed that the rational numbers, the fractions, every number you can write as one integer divided by another, are also the same size infinity as the counting numbers. This is less obvious and more surprising. Think about it. Between any two counting numbers, there are infinitely many fractions. Between 0 and 1 alone, there's 1/2, 1/3, 1/4, 2/3, 3/7, and on and on and on, without end. It seems like there should be vastly more fractions than counting numbers. But Cantor found a way to list them. He arranged them in a clever zigzag pattern, a diagonal grid where you list all fractions with numerator and denominator, adding up to 2, then 3, then 4, and so on. And he showed that you could create a sequence that hits every single rational number exactly once. You could match them up with the counting numbers, 1 to 1, nothing left over, same size infinity. So at this point you might be thinking, well, maybe all infinities are the same size. Maybe infinity is just infinity, and that's that. But here's where Cantor dropped his bombshell. And it's one of the most stunning results in the history of human thought. He proved that the real numbers, the full continuum, every point on the number line, including all the irrational numbers like pi and the square root of 2, are a bigger infinity than the counting numbers. Fundamentally, uncountably, irreducibly bigger. No matter how clever you are, no matter what matching scheme you try, you cannot put the real numbers into one-to-one correspondence with the counting numbers. There will always be real numbers left over. Always. The proof is called the diagonal argument, and it's so elegant that it almost feels like a magic trick. Here's how it works. Suppose someone claims they have a complete list of all real numbers between 0 and 1. Every single one matched up with a counting number, number 1 on the list, number 2, number 3, and so on. Cantor says, "Fine, show me your list." And then he constructs a new number that's definitely between 0 and 1, but definitely not on your list. He does it digit by digit. For the first digit of his new number, he looks at the first digit of the first number on your list and picks something different. For the second digit, he looks at the second digit of the second number and picks something different. For the third digit of the third number, something different, and so on, all the way down the diagonal of your list. The number he builds this way can't be the first number on your list because it differs in the first digit. It can't be the second number because it differs in the second digit. It can't be the nth number because it differs in the nth digit. It's not anywhere on your list. So your list wasn't complete after all. And this works no matter what list you come up with. Every possible listing of real numbers has gaps. The real numbers are simply too numerous to be listed, too vast to be corralled into a sequence. Cantor called the infinity of the counting numbers Aleph Null, Aleph being the first letter of the Hebrew alphabet, and the infinity of the real numbers something strictly larger. And he went further, showing that you can always build a bigger infinity from any infinity you already have, which means there isn't just one infinity or two. There's an infinite tower of infinities, each one incomprehensibly larger than the last. This was too much for some of his contemporaries. Leopold Kronecker, one of the most influential mathematicians of the era and a powerful figure at the University of Berlin, was openly hostile. Kronecker believed that mathematics should be grounded in the counting numbers and nothing else. He famously said, "God made the integers. All else is the work of man." And he saw Cantor's work as dangerous nonsense. He called Cantor a corrupter of youth. He blocked Cantor's publications and his career advancement. Henri Poincaré, another giant of mathematics, called Cantor's set theory a disease from which mathematics would eventually recover. It didn't recover. It absorbed it. Cantor's ideas became the foundation of modern mathematics. Set theory, the framework he built, is now the bedrock on which virtually everything else rests. But Cantor himself paid a terrible price. He suffered from severe bouts of depression throughout his later life, spent time in sanatoriums, and died in 1918 in a psychiatric clinic in Halle. Whether the professional attacks contributed to his mental illness is something historians debate. But it's hard to read his story without feeling the weight of it. Here was a man who saw further into the nature of infinity than anyone before him, and the world punished him for it. But the ideas survived, and they lead to something that might seem paradoxical at first, something that connects back to a question you might have had without even realizing it. If the real numbers are uncountably infinite, and the rational numbers are only countably infinite, then what are all those extra real numbers? What's filling in the gaps between the fractions? The answer is the irrational numbers, numbers that can't be written as fractions, numbers whose decimal expansions go on forever without repeating. And the strange, almost unsettling truth is that almost all real numbers are irrational. The rationals, despite being infinite, are sparse, scattered like stars in a vast dark sky. The irrationals are the darkness itself, filling every gap, every crevice, every infinitesimal space between one fraction and the next. If you could somehow pick a real number at random from the number line, truly at random, with perfect uniformity, the probability of picking a rational number would be exactly 0. Not small, 0. The rationals are, in a precise mathematical sense, negligible. They're a set of measure 0, a phrase that sounds almost dismissive, like you're saying those numbers don't matter. But that's not quite what it means. Measure 0 doesn't mean the set is empty. It doesn't mean the rationals aren't there. It means that if you were to stretch a kind of mathematical net over the number line, if you tried to cover all the rational numbers with tiny little intervals, you could make the total length of those intervals as small as you like, arbitrarily small. You could cover every single rational number on the entire number line with intervals whose combined length adds up to less than 1/billionth of a unit, or less than a trillionth, or less than any positive number you care to name. That's what measure 0 means. The rationals can be corralled, contained, squeezed into an impossibly thin covering, because even though there are infinitely many of them, they're countably infinite. You can list them. And because you can list them, you can assign the first one an interval of width 1/2 epsilon, the second one an interval of width 1/4 epsilon, the third one an interval of width 1/8 epsilon, and so on, where epsilon is any tiny positive number you choose. Add up all those widths. It's a geometric series, and it converges to epsilon. So the total coverage is as small as you want. And this is where the idea of measure starts to feel like something genuinely profound, because it gives you a way to talk about the size of a set that's completely different from counting. Counting says the rationals are infinite. Measure says they're negligible. Both statements are true. They're just answering different questions. Counting asks, how many elements? Measure asks, how much space do they take up? And for the rationals, the answer to the second question is essentially none. This idea, this notion of measure, was made rigorous by a French mathematician named Henri Lebesgue in the early 1900s. And Lebesgue's story is one of those beautiful cases where someone takes a practical problem and, in solving it, opens up an entirely new wing of mathematics. The practical problem was integration. You remember integration from calculus, probably. The idea of finding the area under a curve. Riemann, the same Riemann we've already encountered, had developed a perfectly good theory of integration in the 1850s. It worked for most functions people cared about. But there were these weird, pathological functions. Functions that were discontinuous at every rational point, or functions defined in bizarre, piecewise ways, where Riemann's integral just broke down. It couldn't handle them. And as mathematicians in the late 1800s started constructing more and more of these strange creatures, it became clear that a more powerful theory was needed. Lebesgue, born in 1875 in Beauvais, France, figured it out. His key insight was to flip the way you think about integration. Instead of slicing up the x-axis into thin vertical strips, which is what Riemann's approach does, Lebesgue sliced up the y-axis. He asked, for each possible output value, how much of the input gives you roughly that output? And to answer that question, he needed a way to measure the size of arbitrary sets of real numbers. Not just intervals, but weird, complicated, dust-like sets. Sets like the rationals. Sets like the irrationals. Sets that Riemann's theory couldn't handle because it had no way to measure them. So Lebesgue developed his theory of measure, building on earlier ideas from Émile Borel and others, and used it to construct a new integral, the Lebesgue integral, that was strictly more powerful than Riemann's. Every function that was Riemann integrable was also Lebesgue integrable. But there were functions that only Lebesgue's theory could handle. It was a strictly better tool. And at the heart of it was this concept of measure, this way of assigning a size to sets that went far beyond just counting their elements or measuring their length in the ordinary sense. Now, I realize this might sound abstract, and it is abstract. But here's why it matters in the real world. Lebesgue's integral is the foundation of modern probability theory. When you hear about probability distributions, expected values, statistical mechanics, signal processing, quantum mechanics, all of that machinery runs on Lebesgue integration. The reason your phone can compress audio files, the reason weather models can handle continuous probability distributions, the reason financial mathematics can price options, all of it traces back to this French mathematician's decision to slice things horizontally instead of vertically. It's one of those cases where a purely theoretical advance, motivated by pathological counterexamples that seem to have no practical use, turned out to be exactly what the applied sciences needed 50 years later. But let's come back to the number line for a moment, because there's something else hiding in there that's worth talking about. We've established that the irrationals vastly outnumber the rationals, that they fill up essentially all of the real number line. But the irrationals themselves aren't all the same. There are different kinds of irrational numbers, and the distinction between them leads to one of the most beautiful and underappreciated ideas in all of mathematics. Some irrational numbers are algebraic. That means they're solutions to polynomial equations with integer coefficients. The square root of 2 is irrational. We've known that since the ancient Greeks. But it's algebraic because it's a solution to the equation x squared equals 2. The golden ratio is irrational but algebraic. The cube root of 7, irrational but algebraic. These numbers can't be written as fractions, but they can be captured by polynomial equations. They're wild, but they're not completely untamed. And then there are the transcendental numbers. These are numbers that aren't the solution to any polynomial equation with integer coefficients. They're not roots of any algebraic equation, no matter how complicated. They transcend algebra. That's literally what the name means. And the first examples that were proven to be transcendental are numbers you know well. Pi is transcendental. Euler's number, E, is transcendental. These aren't just irrational. They're a deeper kind of irrational, unreachable, by the tools of algebra. The existence of transcendental numbers was first proved by Joseph Liouville in 1844, and he did it by constructing a specific example, a number now called Liouville's constant, that he could prove wasn't the root of any polynomial. It's a number whose decimal expansion has ones in the factorial positions: position 1, position 2, position 6, position 24, position 120, and zeros everywhere else. A strange, sparse number, deliberately designed to be so well approximated by rationals that no polynomial could pin it down. But here's the thing that really gets interesting. In 1874, the same year Cantor was doing his groundbreaking work on the sizes of infinity, Cantor proved something remarkable about transcendental numbers. He showed that the algebraic numbers, despite seeming like they should be more numerous because they include all the rationals plus all those irrational roots, are actually countable. You can list them. There are only countably many algebraic numbers. And since the real numbers are uncountable, that means the transcendental numbers must be uncountable. Almost all real numbers are transcendental. The algebraic numbers, like the rationals, are a set of measure zero. They're the exception, not the rule. Think about what that means for a second. Pi and E, the two most famous transcendental numbers, are famous precisely because they show up everywhere in mathematics and physics. But they're not special in being transcendental. They're special in being transcendental numbers we can actually name and work with. The overwhelming majority of transcendental numbers are numbers we'll never write down, never compute, never even describe. They're just there, filling up the number line, anonymous, and uncountable. And yet, proving that any specific number is transcendental is incredibly hard. It took until 1873 for Charles Hermit to prove that E is transcendental, and another 9 years until 1882 for Ferdinand von Lindemann to prove the same for pi. Lindemann's proof, by the way, had a spectacular consequence. It settled one of the oldest open problems in mathematics, the question of squaring the circle. The ancient Greeks had asked whether, given a circle, you could construct a square with the same area using only a compass and straight edge. People had been trying for over 2,000 years, and Lindemann's proof that pi is transcendental showed, in one stroke, that it's impossible. You simply cannot do it. The tools of compass and straight edge can only construct algebraic numbers, and since pi is transcendental, you can never construct a square with area exactly equal to pi r squared using those tools. 2 millennia of attempts, and the answer was no. Not, we haven't found a way yet. No, it's provably impossible. That word, impossible, is one of the most powerful words in mathematics, and it shows up more often than you might expect. Mathematics isn't just about proving what's true. It's about proving what can't be done. And that brings us to something that shook mathematics to its very core in the 20th century. Something that changed not just what mathematicians believed, but how they thought about the nature of mathematical truth itself. To understand it, we need to go back to the turn of the 20th century, when mathematics was in a kind of crisis. Not a crisis of results. Results were pouring in from set theory, from topology, from analysis, from algebra. The crisis was about foundations. What, exactly, was mathematics built on? What were the basic rules? And could those rules ever lead to a contradiction? The worry wasn't idle. Cantor's set theory, for all its brilliance, had a problem. In 1901, Bertrand Russell, the British philosopher and logician, discovered a paradox that struck at the heart of naive set theory. It's called Russell's paradox, and it's deceptively simple. Consider the set of all sets that don't contain themselves. Does this set contain itself? If it does, then by definition it shouldn't. If it doesn't, then by definition it should. It's a contradiction either way. And if your foundational theory of mathematics allows contradictions, then in principle you can prove anything. True statements, false statements, anything. The whole edifice crumbles. Russell's paradox sent shockwaves through the mathematical community. It meant that the naive, intuitive notion of a set, just any collection of objects you can describe, was broken. You couldn't just define sets willy-nilly. You needed rules, axioms, careful restrictions on what counted as a legitimate set, and this launched an enormous project to put mathematics on a firm, rigorous, axiom-based foundation. David Hilbert, the towering German mathematician who was arguably the most influential figure in mathematics at the turn of the century, took this project personally. Hilbert believed, passionately, almost religiously, that mathematics could be made completely rigorous. He wanted a system of axioms from which all mathematical truths could be derived, a system that was consistent, meaning it would never produce contradictions, and complete, meaning every true statement could be proved within the system. He laid out this vision explicitly in 1900 in his famous list of 23 unsolved problems presented at the International Congress of Mathematicians in Paris, and he returned to it again and again throughout his career. Hilbert wanted certainty. He wanted to know that mathematics was safe, that its foundations were solid, that no paradox could ever creep in from some forgotten corner and bring the whole thing tumbling down. And for a while, for about 3 decades, it really seemed like he might get his wish. Hilbert's program, as it came to be called, attracted some of the sharpest minds in the world. The idea was intoxicating, that you could reduce all of mathematics to a finite set of axioms and mechanical rules of inference, and that from those axioms you could, at least in principle, derive every true mathematical statement. No gaps, no mysteries, just logic, all the way down. And look, you can understand why that vision was so appealing. Think about what mathematics had been through by that point. You had the crisis with non-Euclidean geometry in the 19th century, where people realized that the parallel postulate, this thing everyone had assumed was obviously true for 2,000 years, could be replaced with alternatives that produced perfectly consistent, perfectly valid geometries. You had Cantor's infinities, which half the mathematical world found deeply unsettling. You had Russell's paradox blowing a hole in set theory. Every time mathematicians thought they were standing on bedrock, the ground shifted. Hilbert wanted to stop the shifting once and for all. So the work proceeded. Ernst Zermelo and Abraham Fraenkel developed a careful axiomatic system for set theory, what we now call ZFC, Zermelo-Fraenkel set theory with the axiom of choice, that avoided Russell's paradox by being very precise about which sets you were allowed to construct. Russell himself, along with Alfred North Whitehead, spent years writing Principia Mathematica, this massive 3-volume work that attempted to derive all of mathematics from pure logic. It famously takes them several hundred pages just to prove that 1 + 1 = 2. Which sounds absurd, and honestly it kind of is, but the point wasn't efficiency. The point was absolute rigor. Every single step had to be justified from the ground up, and Hilbert kept pushing. In the 1920s, he refined his program into something more specific. He wanted 3 things. First, consistency, a proof that mathematics would never contradict itself. Second, completeness, a guarantee that every true statement could be proved. And third, decidability, an algorithm, a mechanical procedure that could take any mathematical statement and determine, in a finite number of steps, whether it was true or false. That last one is called the Entscheidungsproblem, German for decision problem. And Hilbert considered it one of the great open questions of mathematics. Now, here's the thing. Hilbert was so confident that all of this was achievable that he made it a kind of rallying cry. He had this famous motto, Wir müssen wissen, wir werden wissen. We must know, we will know. He said it in a radio address in Königsberg in 1930. It's actually inscribed on his tombstone. And the irony, the deep, almost tragic irony, is that the very day before Hilbert gave that speech, in the very same city, at a conference Hilbert attended, a quiet, young, 24-year-old Austrian logician named Kurt Gödel stood up and calmly announced that he had proved Hilbert's program was impossible. Let that sink in for a moment. The day before Hilbert declared, "We will know," Gödel showed that there are things we can never know. Not because we're not smart enough, not because we haven't found the right tools yet, but because of the fundamental nature of mathematical systems themselves. Kurt Gödel is one of the most fascinating figures in the history of thought, full stop. He was born in 1906 in Brunn, which was then part of Austria-Hungary and is now Brno in the Czech Republic. He was a brilliant student, deeply introverted, and from an early age, he was drawn to the most abstract questions about logic and the foundations of mathematics. He moved to Vienna, fell in with the intellectual circle around the Vienna Circle, the famous group of philosophers and logicians, though he never fully agreed with their philosophical positions. And in 1930 and 1931, while still in his mid-20s, he published two theorems that changed everything. They're called Gödel's incompleteness theorems, and they are among the most profound results in the history of mathematics. Let me try to explain them in a way that captures the essence without getting lost in the technical machinery, because the ideas themselves are actually quite beautiful once you see what's going on. The first incompleteness theorem says this: in any consistent formal system that is powerful enough to describe basic arithmetic, addition and multiplication of natural numbers, there will always be true statements that cannot be proved within that system. Always. No matter how clever your axioms are, no matter how many axioms you add, there will always be truths that slip through the net. The system is necessarily incomplete. Now, let's unpack that slowly, because every word matters. First, consistent, meaning the system doesn't contradict itself. If a system is inconsistent, you can prove anything, so consistency is the bare minimum you need. Second, powerful enough to describe basic arithmetic. This isn't about some weird exotic system. This is about any system that can handle the natural numbers. That's essentially all of mathematics as we know it. And the conclusion is devastating for Hilbert's program. Completeness is impossible. You cannot have a consistent system that proves all true statements about arithmetic. There will always be gaps. Here's what's really clever about how Gödel proved it. He essentially constructed a mathematical statement that says, this statement cannot be proved in this system. Think about that. If the statement is true, then it can't be proved, which means the system is incomplete because there's a true statement it can't prove. If the statement is false, then it can be proved. But that means the system proved something false, which means the system is inconsistent. So either way, you're stuck. Either your system is incomplete or it's inconsistent. And if you're committed to consistency, which you have to be because an inconsistent system is worthless, then incompleteness is the price you pay. It's a bit like the liar's paradox. This sentence is false, but Gödel made it rigorous. He figured out a way to encode statements about a formal system within the system itself, using a technique now called Gödel numbering. Every symbol, every formula, every proof gets assigned a unique number, and then statements about proofs become statements about numbers, which the system can talk about. It's an act of extraordinary ingenuity, turning a system's gaze inward, making it examine itself, and showing that self-examination inevitably produces blind spots. The second incompleteness theorem is, if anything, even more devastating. It says that a consistent formal system powerful enough to describe basic arithmetic cannot prove its own consistency. Read that again. You can't prove, from within mathematics, that mathematics is consistent. The very thing Hilbert wanted most, a proof that the system wouldn't contradict itself, is the one thing the system can never provide for itself. Now, does this mean mathematics might be inconsistent? Not necessarily. Most mathematicians believe arithmetic is consistent. We've been using it for thousands of years without finding a contradiction, and there are good reasons to think one won't show up. But Gödel showed that this belief can never be converted into a proof from within the system. It's an article of faith, in a sense. Or at least, any proof of consistency would have to come from a stronger system, whose own consistency you then need to prove, and you're off on an infinite regress. Think about what this meant for Hilbert. His entire program, the dream of a complete, consistent, decidable mathematics, was shattered in one stroke. And Hilbert, by most accounts, was not happy about it. Some historians suggest he was initially furious, though he eventually came to accept the result. The mathematical community as a whole took a while to absorb the implications. Some people tried to find loopholes, ways around the theorems, alternative frameworks that might escape Gödel's conclusions. But the theorems held. They've been reproved, extended, analyzed from every conceivable angle, and they stand as solid today as they did in 1931. And here's something worth sitting with. Gödel's theorems don't mean mathematics is broken. They don't mean we can't do mathematics, or that our proofs are unreliable, or that everything is uncertain. What they mean is that mathematics is inexhaustible. There will always be more to discover, always true things that lie beyond the reach of any particular set of axioms. In a strange way, it's almost liberating. Mathematics isn't a finite building that can be completed. It's an open landscape that extends forever. But the story doesn't end with Gödel, because remember Hilbert's third requirement, decidability, the Entscheidungsproblem. Gödel's theorems showed that not every true statement can be proved, but they left open the question of whether there might still be a mechanical procedure that could at least tell you, for any given statement, whether a proof exists. Maybe you can't prove everything, but can you at least sort statements into provable and not provable? In 1936, two people independently answered this question, and the answer was no. One of them was Alonzo Church, an American mathematician at Princeton. The other was Alan Turing, a young British mathematician who was, at the time, a graduate student. And Turing's approach is the one that changed the world, because in order to prove that the decision problem was unsolvable, he had to first define precisely what a mechanical procedure even meant. And in doing so, he invented the concept of what we now call a Turing machine. This is one of those moments where a question about pure mathematics, about logic and provability and the limits of formal systems, accidentally gives birth to something enormously practical. Turing wasn't trying to invent the computer. He was trying to prove a theorem about the foundations of mathematics. But to do it, he needed to formalize the idea of computation itself, and the abstract machine he described, a simple device that reads and writes symbols on an infinite tape according to a finite set of rules, turned out to be the theoretical blueprint for every digital computer that has ever existed. Turing showed that there are problems that no Turing machine can solve. The most famous is the halting problem. Given a program and an input, can you determine in advance whether the program will eventually stop or run forever? Turing proved that no general algorithm can answer this question for all possible programs. It's undecidable. And from this, it follows that Hilbert's Entscheidungsproblem is also unsolvable. There is no mechanical procedure that can determine the truth or falsity of every mathematical statement. So by 1936, all three pillars of Hilbert's program had fallen. Mathematics cannot be proved consistent from within. Mathematics cannot be complete, and mathematics cannot be decided by an algorithm. The dream of total certainty, of a finished, polished, self-contained mathematical edifice, was gone. And yet, and this is the part I find really beautiful, mathematics kept going. It didn't collapse. It didn't fall into crisis and never recover. Mathematicians absorbed these limitations and kept working, kept proving theorems, kept building extraordinary structures of thought. Because Gödel's theorems tell you about the boundaries of formal systems, but within those boundaries, there is still an unimaginable richness to explore. It's a bit like learning that the universe is finite but unbounded, You can't reach the edge, but there's more than enough space to spend a lifetime exploring. And speaking of exploration, there's another deeply confusing idea in mathematics that connects to everything we've been talking about: the axiom of choice. I mentioned it briefly when we talked about Zermelo-Fraenkel's set theory, but it deserves a closer look because it's one of those principles that sounds completely obvious at first, and then turns out to have consequences that are genuinely strange. Genuinely, deeply strange. Like, strange enough that some very serious mathematicians refuse to accept it, and others built entire alternative frameworks just to avoid it. So let's talk about what it actually says. The axiom of choice states roughly that if you have a collection of non-empty sets, you can always form a new set by picking exactly one element from each of them. That's it. That's the whole thing. You have a bunch of bins. Each bin has at least one thing in it, and you're allowed to reach into each bin and grab one thing. Sounds completely reasonable, right? Almost trivially obvious. If the bins are full, of course you can pick from them. What could possibly go wrong? Well, here's the thing. When you're dealing with a finite number of bins, or even a countably infinite number of bins where you have some rule for choosing, like always pick the smallest number, there's no issue at all. You don't even need the axiom. You can just do it. The trouble starts when you have an uncountably infinite collection of sets, and no rule, no recipe, no algorithm for making the choices. The axiom of choice says you can still do it. You can still form that set of chosen elements, even if you can't describe how you'd go about choosing. It asserts the existence of a selection without providing any method for making it. And that distinction between existence and construction is where the philosophical earthquake begins. Ernst Zermelo first formally stated the axiom of choice in 1904, and he did it for a very specific reason. He wanted to prove something called the well-ordering theorem, which says that every set can be well-ordered, meaning you can arrange its elements so that every non-empty subset has a least element. For the natural numbers, this is obvious. 1, 2, 3, 4, there's always a smallest. But for the real numbers, can you arrange all the real numbers, all those uncountable, infinitely many points on the number line, into a sequence where every subset has a first element? That seems absurd. Nobody can actually describe such an arrangement. But Zermelo proved it must exist using the axiom of choice. The reaction was immediate and fierce. Henri Poincaré, one of the greatest mathematicians of the era, was skeptical. Émile Borel, a brilliant French mathematician whose work on measure theory we touched on earlier, outright rejected it. Their objection wasn't that the axiom led to contradictions. It was that it asserted the existence of objects that could never be explicitly constructed. To them, this was a kind of mathematical cheating. If you can't build it, if you can't point to it, if you can't describe it, in what sense does it exist? This is one of those moments where mathematics bumps up against philosophy in a way that's impossible to separate. What does it mean for a mathematical object to exist? Is it enough to show that its non-existence leads to a contradiction? Or do you actually have to construct it? These aren't idle questions. They divided the mathematical community for decades, and in some sense, they still do. Now, you might be thinking, okay, but does it matter? If the axiom of choice is just about picking elements from sets, how consequential can it really be? And the answer is wildly, almost absurdly consequential. The axiom of choice is equivalent to a whole constellation of important mathematical statements. The well-ordering theorem is one. Zorn's lemma is another. And if you've taken any abstract algebra, you've probably seen Zorn's lemma invoked to prove that every vector space has a basis, or that every ring has a maximal ideal. These are foundational results. Without the axiom of choice, huge swaths of modern mathematics become much harder or simply unavailable. But here's where it gets really wild. In 1924, two Polish mathematicians, Stefan Banach and Alfred Tarski, used the axiom of choice to prove something that sounds like it should be illegal. They showed that you can take a solid ball in three-dimensional space, decompose it into a finite number of pieces, and then reassemble those pieces using only rigid motions, just rotations and translations, into two solid balls, each identical in size to the original. Two balls from one, same size, no stretching, no gaps, no overlaps, just cutting and rearranging. This is the Banach-Tarski paradox, and when people first hear it, the reaction is almost always the same. That can't be right. That violates conservation of volume. That violates basic physics. That violates common sense. And in a way, it does. But the key is in the nature of those pieces. The pieces you cut the ball into are not ordinary geometric shapes. They're not things you could ever physically create. They are infinitely complicated, fractal-like, non-measurable sets. Sets so wild and scattered that the concept of volume simply doesn't apply to them. They don't have a well-defined measure. You can't assign them a size. And because they have no meaningful volume, there's no conservation law being violated. You're rearranging pieces that are, in a sense, so pathological that the usual rules of measurement break down completely. And here's the kicker. The existence of these non-measurable sets depends on the axiom of choice. Without it, you can't prove they exist. In fact, there are models of set theory without the axiom of choice where every set of real numbers is measurable, where the Banach-Tarski paradox simply cannot happen. So the axiom of choice is what opens the door to these bizarre constructions. It gives you incredible power, the power to prove that every vector space has a basis, that products of compact spaces are compact, that surjections have right inverses. But the price you pay is that your mathematical universe contains these strange, non-constructive, almost ghostly objects that defy geometric intuition. So mathematicians had a genuine decision to make. Do you accept the axiom of choice and live with the weirdness? Or do you reject it and lose a huge number of useful theorems? Most mathematicians in practice accepted it. It became part of the standard foundation. ZFC, Zermelo-Fraenkel with choice, which is what most working mathematicians use today, often without even thinking about it. But the debate never fully went away. And in 1938, Gödel, yes, the same Gödel, proved something remarkable. He showed that if ZF set theory without the axiom of choice is consistent, then ZFC with the axiom of choice is also consistent. In other words, adding the axiom of choice doesn't introduce any new contradictions. You can't use it to break mathematics. Then, in 1963, Paul Cohen proved the converse direction, that the negation of the axiom of choice is also consistent with ZF, meaning you can't prove the axiom of choice from the other axioms, and you can't disprove it either. It's independent. It's genuinely optional. Think about what that means for a second. One of the most useful and most controversial principles in all of mathematics is something that the standard axioms can neither confirm nor deny. It floats in a kind of limbo. You can take it or leave it, and either way, you get a perfectly consistent mathematical universe. But the two universes look very different. In one, every vector space has a basis, and the Banach-Tarski paradox is real. In the other, every set of reals might be measurable, but you lose a lot of algebraic structure. Paul Cohen, by the way, deserves a moment here. He was a remarkable figure, largely self-taught in logic, working at Stanford, and he developed an entirely new technique called forcing to prove his independence result. Forcing is a method for constructing new models of set theory, essentially building custom-made mathematical universes with specific properties. It was so powerful and so original that it earned Cohen the Fields Medal in 1966, and it remains one of the most important tools in set theory to this day. Cohen was an analyst by training, not a logician, and the fact that he came into the field as something of an outsider and solved one of the biggest open problems in foundations, a problem that had been open for decades, is one of those stories that reminds you how unpredictable mathematical progress can be. And this idea of independence, of statements that are neither provable nor disprovable, connects beautifully back to Gödel's incompleteness theorems. Gödel showed that any sufficiently powerful formal system contains undecidable statements. The axiom of choice turned out to be one of them, at least relative to ZF. But it's not the only one. There's another statement, even more famous in some ways, that also turned out to be independent of ZFC, and it connects directly to Cantor's work on infinity that we talked about earlier. Remember Cantor's diagonal argument? He showed that the real numbers are uncountable. There are strictly more reals than natural numbers. The cardinality of the naturals is Aleph null, and the cardinality of the reals is strictly larger. But Cantor asked a natural follow-up question. Is there a set whose cardinality is strictly between Aleph null and the cardinality of the reals? Is there an infinity that's bigger than the integers, but smaller than the reals? He believed the answer was no, that the reals are the very next size of infinity after the naturals. This belief is called the continuum hypothesis. Cantor spent years trying to prove it. He couldn't. It tormented him, contributed to his mental health struggles, and he never resolved it. Hilbert listed it as the very first problem on his famous 1900 list of 23 open problems, the most important unsolved questions in mathematics. And for decades, nobody could prove it or disprove it. Then Gödel, in 1940, showed that the continuum hypothesis is consistent with ZFC. You can't disprove it. And Cohen, in 1963, using that same forcing technique, showed that its negation is also consistent with ZFC. You can't prove it either. The continuum hypothesis is independent of ZFC. It's another statement that floats in that strange logical space where standard mathematics simply has nothing to say about it. You can assume it's true, or you can assume it's false, and either way, you get a perfectly valid mathematical framework. Now, this might feel unsettling. You might be thinking, wait, is there a set between the integers and the reals, or isn't there? Surely it's one or the other, and that's a completely natural reaction, but it reveals something profound about the nature of mathematical truth. In the standard axiomatic framework, there simply isn't enough information to determine the answer. It's not that we haven't been clever enough to find the proof. It's that the proof doesn't exist within the system. The question is genuinely undecidable. Some mathematicians find this liberating. Others find it deeply troubling. And there's an active research program, even today, trying to find new axioms beyond ZFC, that might settle the continuum hypothesis one way or the other. The set theorist Hugh Wooden, for instance, has spent decades developing a framework involving large cardinal axioms and a principle he calls the ultimate L, which he believes points toward the continuum hypothesis being false. Others disagree. The debate is very much alive. And what I find so beautiful about all of this is how it circles back to the very beginning of our story. Remember the Sumerians, pressing wedge-shaped marks into clay tablets, just trying to keep track of grain and livestock? They were building the first number systems, the first formal representations of quantity. And from that humble beginning, mathematics grew and grew, through zero, through negatives, through irrationals and imaginaries, through Cantor's infinities, through the foundational crisis, through Gödel and Turing, all the way to this point where we're asking whether the axioms themselves are sufficient to answer our questions. The tools got more powerful, the questions got deeper, and the surprises never stopped coming. But there's another thread I want to pick up now, because we've been spending a lot of time in the abstract, in logic, in set theory, in foundations, and I want to bring us back to something that feels more tangible, more visceral. I want to talk about calculus, and specifically about the part of calculus that confuses almost everyone when they first encounter it, the part that confused the greatest mathematicians in history for 200 years before it was finally made rigorous. I want to talk about limits, the idea of a limit. And I know, if you've taken a calculus class, you probably remember some notation, maybe a formula or two, maybe a teacher saying something about approaching but never reaching. But the concept underneath all of that is one of the most slippery, counterintuitive, and genuinely profound ideas in all of mathematics. And the story of how we finally pinned it down is one of my favorites. So let's set the stage. It's the late 1600s. Isaac Newton in England and Gottfried Wilhelm Leibniz in Germany have both, more or less independently, invented calculus. And calculus works. That's the remarkable thing. Newton is using it to describe the motion of planets, the trajectories of cannonballs, the way light bends through a prism. Leibniz is developing elegant notation, much of which we still use today, by the way, and applying it to problems in geometry and physics. The results are spectacular. Calculus lets you calculate areas under curves, find the slopes of tangent lines, describe rates of change, solve differential equations that model the physical world. It's arguably the most powerful mathematical tool ever invented. But here's the thing. Neither Newton nor Leibniz can fully explain why it works. At the heart of their methods is a quantity they call an infinitesimal, an infinitely small number, not zero, but smaller than any positive number you can name. Newton calls these fluxions and talks about quantities that are evanescent, vanishing. Leibniz uses the notation dx and diy, treating them as infinitely small increments. And the way they do calculus is essentially this. You manipulate these infinitesimals as if they're real numbers. You do your algebra, you get your answer, and then at the end, you throw away any remaining infinitesimal terms because they're too small to matter. And the answers you get are correct. They match physical reality. They solve real problems. But the logical foundation is, well, it's a mess. Think about what they're actually claiming. An infinitesimal is supposed to be a number that's greater than zero, but smaller than every positive fraction. Smaller than 1/10, smaller than 1/1,000,000th, smaller than 1 over a googolplex. Is that even a coherent idea? And when you divide by an infinitesimal, which is something you do constantly in calculus, that's essentially what a derivative is. You're dividing by something that's almost zero, but not quite. And then later you treat it as if it is zero. So which is it? Is it zero or isn't it? This bothered people. It bothered people a lot. The most famous critic was the Irish philosopher George Berkeley, who in 1734 published a delicious little pamphlet called the analyst. And Berkeley was not a mathematician. He was a bishop, actually. But he was sharp, and he saw the logical problem clearly. He called infinitesimals the ghosts of departed quantities. That phrase is just perfect, isn't it? The ghosts of departed quantities. His argument was essentially, you mathematicians mock theologians for believing in mysteries, but your own calculus is built on a concept that's just as mystical and contradictory as anything in theology. You treat these infinitesimals as non-zero when it's convenient, then you treat them as zero when that's convenient, and you call this rigorous reasoning. And the uncomfortable truth was that Berkeley had a point. The results of calculus were correct, but the reasoning was shaky. Mathematicians knew it, and for the next century and a half, the best minds in Europe tried to fix the problem. Now, let me give you a concrete example so you can feel the confusion in your bones. Think about the derivative of a simple function, say x squared. You want to find the rate at which x squared is changing at any given point. The way Newton and Leibniz would do it is, take x, increase it by a tiny amount h, compute the new value, that's x plus h, all squared, which is x squared plus 2xh plus h squared. Subtract the original value, x squared, and you get 2xh plus h squared. Now divide by h, and you get 2x plus h. And now, here's the magic trick. Let h go to 0, and you're left with 2x. The derivative of x squared is 2x. But wait, you divided by h. You can't divide by 0. That's one of the most fundamental rules in mathematics. So h can't be 0 when you divide, but then you set h equal to 0 at the end. So h is simultaneously not 0 and 0? That's the ghost of the departed quantity right there. This is what needed to be resolved, and the resolution came slowly, in stages, through the work of several mathematicians across the 18th and 19th centuries. The key figures are Jean-Laurent d'Alembert, Augustin-Louis Cauchy, and Karl Weierstrass, and each one brought the idea of a limit into sharper and sharper focus. D'Alembert, writing in the 1750s, was one of the first to suggest that the fundamental concept of calculus should be the limit, not the infinitesimal. He argued that when we talk about a derivative, we're really talking about the limit of a ratio, the value that the ratio approaches as the increment gets smaller and smaller. He didn't have a precise definition of what approaches meant, but he had the right intuition. He was pointing in the right direction. Then came Cauchy, and this is where things start to crystallize. Augustin-Louis Cauchy was a French mathematician working in the early 1800s, and he was prolific, almost absurdly so. He published over 800 papers in his lifetime. He was also, by many accounts, not the easiest person to get along with. He was deeply conservative, deeply Catholic, politically royalist in post-revolutionary France, and he had a tendency to step on other mathematicians' work without proper credit. But his contributions to analysis, the branch of mathematics that puts calculus on rigorous footing, were monumental. In his 1821 textbook, The Cours d'Analyse, Cauchy gave a definition of limit that was a huge step forward. He wrote something like, when the values successively attributed to a variable approach a fixed value indefinitely in such a way that they end up differing from it by as little as desired, that fixed value is called the limit. Do you hear what he's doing there? He's replacing the mystical idea of an infinitesimal with a process, the process of getting closer and closer. The limit isn't a number you reach. It's a number you can get arbitrarily close to. This is a subtle but crucial shift. Instead of saying h equals 0, you say, for any degree of closeness you demand, I can make h small enough that the ratio gets that close to the limit. You never actually have to set h equal to 0. You just have to show that you can get as close as you want. But even Cauchy's definition, as good as it was, still relied on somewhat intuitive language. Approach. As little as desired. Indefinitely. It was better than what came before, but it wasn't airtight. And making it airtight, that was the achievement of Karl Weierstrass. Weierstrass was a German mathematician, and his story is one of the most unlikely in the history of mathematics. He didn't get his start in academia. He spent years teaching high school, gymnasium, as they called it in Germany, in small provincial towns, teaching arithmetic and penmanship and gymnastics, of all things, to teenagers. He was in his 40s before he published the work that made his reputation. But when he finally entered the mathematical scene in Berlin, he transformed it. What Weierstrass did in the 1860s and 1870s was take Cauchy's intuitive idea of a limit and express it in purely logical, purely quantitative terms. No more approaches, no more as close as desired. Instead, he gave us the epsilon delta definition. And if you've taken a rigorous calculus or analysis course, you've probably encountered this, and it might have made your head spin. But let me walk you through it slowly, because it's actually beautiful once you see what it's doing. Here's the idea. You want to say that the limit of some function f of x, as x approaches some value a, equals some number L. What Weierstrass says is, for every positive number epsilon, and epsilon can be as tiny as you like, 1 over a trillion, 1 over a Google, whatever. For every epsilon, there exists a positive number delta, such that whenever x is within delta of a, but not equal to a, the value f of x is within epsilon of L. Let me say that again more casually. You're playing a game. Your opponent picks a degree of accuracy. That's epsilon. They say, I want f of x to be within this tiny window of L. And your job is to find a corresponding window around that's delta, such that any x in your window lands f of x in their window. If you can win this game, no matter how small they make epsilon, then the limit exists and equals L. That's it. That's the whole definition. No infinitesimals, no ghosts, no mysticism. Just a precise logical statement about the relationship between two quantities. And with this definition, you can prove all the theorems of calculus rigorously. You can prove that the derivative of x squared is 2x. And at no point do you ever have to pretend that something is simultaneously 0 and not 0. You just show that for any epsilon, there's a delta that works. Now, I'll be honest, when students first encounter this, it often feels more confusing than the intuitive version, not less. And that's okay. The epsilon delta definition isn't meant to be intuitive. It's meant to be precise. It's the difference between pointing at something and saying it's over there versus giving exact GPS coordinates. The pointing is easier, but the coordinates are unambiguous. And here's what's really remarkable about what Weierstrass accomplished. Once you have this rigorous definition of a limit, you can build everything else on top of it. Continuity. What does it mean for a function to have no breaks or jumps? You define it in terms of limits, derivatives, the instantaneous rate of change. That's a limit of a ratio. Integrals. The area under a curve. That's a limit of a sum. Infinite series. When does adding up infinitely many terms give you a finite answer? Limits again. The entire edifice of calculus, this incredibly powerful tool that Newton and Leibniz created, finally had a foundation that could bear its weight. But Weierstrass wasn't done just giving us definitions. He also gave us nightmares, because once you have rigorous tools, you can construct rigorous counterexamples, functions that behave in ways no one had imagined possible. And the most famous of these is the Weierstrass function, which he presented in 1872, and which genuinely shocked the mathematical world. Imagine a curve, a function drawn on a plane. Your intuition says that if the curve is continuous, meaning it has no breaks or jumps, then it should be smooth almost everywhere. Maybe it has a few corners, a few sharp points, like the absolute value function has a corner at 0. But surely, for most points along the curve, you should be able to draw a tangent line. You should be able to compute a derivative. Continuous functions should be differentiable almost everywhere. Weierstrass showed that this intuition is completely wrong. He constructed a function that is continuous everywhere. No breaks, no jumps. You can draw it without lifting your pen. But differentiable nowhere. At every single point, the function has no well-defined slope. It's infinitely jagged, infinitely crinkly, at every scale. You zoom in and it never smooths out. It's like a coastline that remains equally ragged no matter how closely you look at it. And actually, that connection isn't a coincidence. Benoit Mandelbrot would later point to exactly this kind of behavior when he developed fractal geometry in the 1970s. The Weierstrass function is, in a very real sense, a fractal before fractals had a name. When Weierstrass presented this function, many mathematicians were horrified. Charles Hermit, the same Hermit who proved that E is transcendental, wrote to a colleague saying he turned away in fear and horror from this lamentable plague of functions with no derivatives. Henri Poincaré called them monsters. They felt like pathologies, like mathematical curiosities that had no business existing. But they did exist, and the rigorous framework of limits and epsilon delta couldn't exclude them. If your definitions allowed these monsters in, then you had to deal with them. And this is something I love about mathematics, the way rigor forces you to confront things you'd rather ignore. The intuitive, hand-wavy version of calculus was comfortable. It matched our physical intuitions. But when you made it precise, you discovered that the mathematical universe was far stranger and wilder than anyone had suspected. Functions that are continuous, but nowhere smooth. Sets that are uncountable, but have measure 0. Curves that fill entire squares. Those are the piano curves from 1890. Continuous curves that pass through every single point in a square. The more precisely you defined your terms, the more surprises came tumbling out. And this connects back to something we talked about much earlier, when we were exploring Cantor's infinities and the way the rational numbers, despite being dense everywhere on the number line, are actually a vanishingly small set compared to the irrationals. Mathematics keeps revealing that our intuitions about size, smoothness, and structure are unreliable guides to what's actually true. The rigorous definitions aren't just pedantic exercises. They're essential tools for navigating a landscape that's far more complex than it appears. But let me bring this back to something practical, because all of this talk about epsilon delta and nowhere differentiable functions might seem incredibly abstract. Here's why it matters. Every time an engineer designs a bridge, every time a physicist models a quantum system, every time your phone calculates a route or your streaming service compresses a video, the mathematics underlying those computations rests on the framework that Cauchy and Weierstrass built. The algorithms work because the theorems are proven, and the theorems are proven because the definitions are precise. Without rigorous limits, you can't rigorously prove that a numerical method converges to the right answer. You can't guarantee that your approximation is good enough. You're just hoping. And in engineering, hope is not a strategy. And there's one more piece of this story I want to tell you, because it involves a question that sounds almost childishly simple, but turns out to be surprisingly deep. It's a question about adding things up, specifically about what happens when you try to add up infinitely many numbers. Because infinite series, as they're called, are everywhere in mathematics and physics and engineering, and the question of when an infinite sum actually makes sense, when it converges to a definite value, is one that took mathematicians centuries to sort out properly. And like everything else we've been talking about tonight, the answer turned out to be far more subtle than anyone initially expected. So let's start with something concrete. Imagine you're adding up fractions: 1/2 plus 1/4 plus 1/8 plus 1/16, and so on, each term exactly half the previous one. You can almost feel intuitively that this sum is heading somewhere. It's creeping toward one. Each new term gets you a little closer, fills in a little more of the gap. Add up 10 terms and you're at something like 0.999. Add up 100 terms and you're so close to one that the difference is unimaginably tiny. And in the rigorous language of limits that Cauchy and Weierstrass gave us, we can say precisely that this infinite series converges to 1. The partial sums get within any epsilon of 1, no matter how small, if you just go far enough. Beautiful. Clean. No controversy there. But now consider a different series. 1 minus 1 plus 1 minus 1 plus 1 minus 1, on and on forever. What does that add up to? Well, if you group the terms one way, 1 minus 1 plus 1 minus 1 plus 1 minus 1, you get 0 plus 0 plus 0, which is 0. But if you group them differently, 1 minus the quantity 1 minus 1 minus the quantity 1 minus 1, you get 1 minus 0 minus 0, which is 1. Same series, 2 perfectly reasonable-looking rearrangements, 2 different answers. So which is it? 0 or 1? And here's what's really wild. In the 18th century, some mathematicians argued the answer was 1/2 by a completely different method. Leonhard Euler, who was probably the most prolific mathematician in history, was perfectly comfortable assigning values to series like this, using techniques that would make a modern analyst wince. And Euler wasn't stupid. Far from it. He had an almost supernatural intuition for mathematics. But he was working before the rigorous framework existed, and so he sometimes got answers that were, let's say, correct in spirit, but not justified by the tools available. The series I just described, 1 minus 1 plus 1 minus 1, is called Grandi's series, after the Italian mathematician Guido Grandi, who discussed it around 1703. And the confusion it generated was genuinely productive, because it forced people to confront a fundamental question. What does it actually mean for an infinite sum to have a value? You can't just add up infinitely many things the way you add up 3 or 4. You need a definition, a precise rule for what the sum means. And the definition that eventually won out, the one Cauchy championed, is exactly what you'd expect given everything we've talked about. It's based on limits. The sum of an infinite series is defined as the limit of the sequence of partial sums, if that limit exists. If the partial sums bounce around forever without settling down, the series diverges. It doesn't have a sum. Period. By that definition, Grandi's series diverges. The partial sums go 1, 0, 1, 0, 1, 0. They never settle down. No limit. No sum. Case closed. And this might seem like mathematicians being unnecessarily strict, but think about why it matters. If you allow yourself to assign values to divergent series willy-nilly, You can prove absolutely anything. You can prove that 1 equals 0. You can prove that 2 plus 2 equals 5. The logical structure of mathematics collapses. The strictness isn't pedantry, it's the immune system of the entire enterprise. But here's where the story gets richer, because even among series that do converge, there are hidden traps that nobody saw coming until the 19th century. And the person who uncovered the most disturbing one was Bernhard Riemann. Yes, the same Riemann who gave us Riemannian geometry, the mathematics that Einstein would later use for general relativity. In 1854, Riemann proved something about infinite series that is genuinely unsettling. It's called the Riemann rearrangement theorem, and it says this: if you have a series that converges conditionally, meaning it converges, but it wouldn't converge if you replaced all the terms with their absolute values, then you can rearrange the terms of that series to make it converge to any number you want, any number at all, or you can rearrange it to diverge to infinity. Just by changing the order you add things up. Let that sink in for a moment. You have a perfectly convergent series. It has a definite sum, but if you shuffle the terms around, you can make it add up to 17, or -3, or 1,000,000, or pi. The sum depends on the order. For finite sums, order doesn't matter. 3 plus 5 plus 2 is the same as 5 plus 2 plus 3. But for infinite sums, order can matter enormously, and the cases where it matters are precisely the conditionally convergent ones. The classic example is the alternating harmonic series: 1 minus 1, half plus 1, third minus 1, quarter plus 1, fifth minus 1, sixth, and so on. This series converges to the natural logarithm of 2, which is about 0.693. But Riemann showed you could rearrange those exact same terms, every single one of them. No additions, no deletions, just a different ordering, and get any real number as the sum. The proof is actually constructive, meaning he didn't just show it was possible, he showed you how to do it. You want the series to sum to, say, 42? Here's a specific rearrangement that gets you there. It's one of those results that feels like it shouldn't be true, like mathematics is playing a trick on you. But it's rock solid, proven rigorously, and it follows inevitably from the definitions. Now, you might be thinking, does this matter outside of pure mathematics? Does anyone actually rearrange infinite series in the real world? And the answer is yes, constantly, though usually without realizing it. Every time a computer evaluates a function using a series expansion, and this happens billions of times a day, in everything from calculating sines and cosines to rendering graphics to simulating weather, the software is adding up terms of a series in some specific order. If the series is absolutely convergent, meaning it would still converge even if you took the absolute value of every term, then order doesn't matter, and you're safe. But if it's only conditionally convergent, then the order you add things up can affect the answer you get. And in numerical computation, rounding errors can effectively scramble the order. This is one of the reasons numerical analysis, the study of how to actually compute things reliably, is its own deep and important field. The pure mathematicians figured out where the dangers are, and the numerical analysts figure out how to navigate them safely. And this brings us to something I find really beautiful about this whole story, which is the way pure abstraction and practical engineering keep feeding each other. Fourier series are maybe the best example of this. Joseph Fourier, working in France in the early 1800s, was studying heat conduction. Very practical problem. How does heat flow through a metal bar? And he made a bold claim. Any function, no matter how wild or jagged, could be represented as an infinite sum of sines and cosines. Smooth, gentle waves, added together in the right proportions, could reproduce any shape at all. This was a staggering claim, and the mathematicians of his day were deeply skeptical. Lagrange, one of the most respected mathematicians alive, essentially blocked Fourier's 1807 paper from being published in the form Fourier wanted because the mathematical justification was insufficient. And Lagrange was right to be cautious because the full story of when and how Fourier series converge turned out to be extraordinarily subtle. It took the rest of the 19th century and much of the 20th to sort it out completely. Dirichlet made important early progress in 1829, proving convergence for functions satisfying certain conditions. But the general question, for exactly which functions does the Fourier series converge, and in what sense, led mathematicians deep into the theory of integration, which is where Lebesgue's work that we talked about earlier becomes essential. Fourier's practical insight was correct in spirit. You really can decompose incredibly complex signals into simple waves, but making it rigorous required the full machinery of modern analysis. And think about where Fourier's idea lives today. Every digital audio file on your phone uses Fourier's insight. When you stream music, the sound is compressed using transforms that are direct descendants of Fourier series. JPEG images, MRI machines, noise-canceling headphones, the analysis of earthquake vibrations, the detection of gravitational waves, all of it rests on this idea that you can break complex signals into simple periodic components, an idea born from studying heat flow in a metal bar. But here's the thing that connects all of this back to the deeper theme we've been tracing all night. Fourier's work, like Newton's calculus before it, worked brilliantly in practice, long before anyone could explain rigorously why it worked. Engineers and physicists used Fourier series to solve real problems, got correct answers, built real things, and then the mathematicians came along and said, wait, we need to understand exactly when this is valid and when it might fail. And in doing so, they discovered entirely new branches of mathematics: measure theory, functional analysis, distribution theory. The quest for rigor didn't just confirm what the engineers already knew, it opened doors to rooms nobody knew existed. And distribution theory is actually a perfect example of this, because it circles back to something we encountered much earlier in our conversation: the question of what counts as a legitimate mathematical object. In the 1920s and 30s, physicists, particularly Paul Dirac, started using something called the delta function. The idea was simple and incredibly useful. Imagine a function that's zero everywhere except at a single point where it's infinitely tall, and somehow the total area under it equals 1. This is obviously nonsense by the classical definition of a function. No actual function can do that, but Dirac used it constantly in quantum mechanics, and it worked. The calculations came out right. The predictions matched experiments. The mathematicians were horrified. In that particular way, mathematicians get horrified when something works but shouldn't, and it was Laurent Schwartz, a French mathematician, who finally resolved the tension in the late 1940s. He developed the theory of distributions, which provided a rigorous framework that included Dirac's delta function as a perfectly legitimate object, not a function in the classical sense, but a new kind of mathematical entity called a distribution, defined not by its values at points, but by how it acts on other functions. Schwartz won the Fields Medal for this work in 1950, and it's a gorgeous example of the pattern we keep seeing. Practitioners push forward using tools that work but aren't fully understood, and then theorists build the framework that explains why those tools work, and in the process, they create something far more powerful and general than what they started with. And this pattern, intuition first, rigor later, and rigor revealing unexpected depth, shows up in one more place I want to take you, because it involves what might be the most famous unsolved problem in all of mathematics. It connects to infinite series, to prime numbers, to the deepest structure of arithmetic itself. And it starts with that same Bernhard Riemann in a single paper he published in 1859, just 8 pages long, that changed everything we thought we knew about prime numbers. Riemann titled it, "On the Number of Primes Less Than a Given Magnitude." And in those 8 pages, he sketched out ideas so far ahead of his time that mathematicians are still working through the implications more than 160 years later. But to understand what Riemann did, you need to feel why prime numbers are so confusing in the first place. And the confusion isn't that primes are hard to define. They're not. A prime number is just a whole number greater than 1 that can only be divided evenly by 1 and itself. 2, 3, 5, 7, 11, 13. Simple enough. The confusion is that primes behave in ways that seem almost deliberately unpredictable. You look at the number line, and the primes are scattered across it in this pattern that feels random, but can't actually be random, because there's nothing random about them. They're completely determined. There's no coin flip involved. 7 is prime, and 8 isn't. And that's just a fact about the structure of multiplication. And yet, if I give you a stretch of numbers, say, the numbers between 10 million and 10 million plus 100, you can't easily predict which ones will be prime without just checking each one. They don't follow a simple formula. They don't show up at regular intervals. Sometimes they cluster together, like 11 and 13, separated by just 2. Sometimes there are enormous gaps between consecutive primes, and as you go further out along the number line, primes get rarer on average, but they never stop appearing entirely. Euclid proved that around 300 BC, there are infinitely many primes. They thin out, but they never vanish. So here's the question that haunted mathematicians for centuries. Is there a pattern? Not a simple formula that generates every prime, because there almost certainly isn't one in any useful sense. But some deeper law governing how primes are distributed? Some way to describe, on average, how many primes you should expect to find below a given number. And people did notice something. A teenager named Carl Friedrich Gauss, and yes, it's that Gauss, he shows up everywhere, noticed around 1792 or 1793, when he was maybe 15 years old, that the density of primes near a large number n seemed to be roughly 1 over the natural logarithm of n. So around the number 1 million, where the natural log is about 13.8, roughly 1 in every 14 numbers is prime. Around 1 billion, where the log is about 20.7, roughly 1 in every 21 numbers is prime. Gauss didn't prove this. He just noticed it by staring at tables of primes, which is an incredible thing for a teenager to do. But this was Gauss, and incredible was kind of his baseline. This observation eventually became the prime number theorem, which wasn't actually proven until 1896, independently by Jacques Adamar and Charles de la Vallée-Poussin. And it says exactly what Gauss guessed. The number of primes less than n is approximately n divided by the natural logarithm of n, and this approximation gets proportionally better and better as n gets larger. That's a beautiful result. It tells you the broad trend, but it doesn't tell you about the fine structure, the fluctuations, the way primes sometimes cluster and sometimes don't, the way the actual count of primes wobbles above and below that smooth estimate. And this is exactly where Riemann comes in. What Riemann realized in that 1859 paper is that you could study prime numbers using a tool from analysis, a function of a complex variable. Remember the complex numbers we talked about early on? Those numbers with a real part and an imaginary part? Riemann took a function that Euler had already studied for real numbers and extended it into the complex plane, and that extension revealed a hidden structure that nobody had suspected. The function is called the Riemann zeta function. For real numbers greater than 1, it's defined as an infinite series. 1 over 1 to the s, plus 1 over 2 to the s, plus 1 over 3 to the s, plus 1 over 4 to the s, and so on forever. When s equals 2, this is the sum of the reciprocals of the perfect squares, 1 plus a quarter plus a ninth plus a 16th, which Euler had shown equals pi squared over 6, that gorgeous unexpected appearance of pi in a problem about whole numbers. When s equals 1, the series becomes the harmonic series, which diverges. It grows without bound. For any real number s greater than 1, the series converges to some finite value. But here's what Riemann did that was so radical. He said, what if s isn't just a real number? What if s is a complex number with a real part and an imaginary part? The series itself only converges when the real part of s is greater than 1. But Riemann showed that you could extend the function using a technique called analytic continuation to define it for almost every complex number. The extended function agrees with the series wherever the series converges, but it's also defined in places where the series would blow up. It's like finding a way to make sense of the function in a much larger domain than the series alone would allow. And the connection to primes? Euler had already discovered this in the 1730s, and it's one of the most stunning identities in mathematics. The zeta function, that infinite sum over all whole numbers, equals an infinite product over all prime numbers. Specifically, the sum of 1 over n to the s, taken over all positive integers n, equals the product over all primes p of 1 divided by 1 minus p to the negative s. Think about what that means. The left side is about all whole numbers. The right side is about only the primes. And they're equal. This identity, Euler's product formula, is the bridge between analysis and number theory, between the continuous world of functions and the discrete world of primes. It's why the zeta function knows about primes. Now, when Riemann extended the zeta function to the complex plane, he discovered that the function equals 0 at certain points. Some of these zeros are easy to find and well understood. They occur at the negative even integers, -2, -4, -6, and so on. These are called the trivial zeros, and they're not very interesting. But Riemann also found that the function has other zeros, infinitely many of them, in a vertical strip of the complex plane, where the real part of s is between 0 and 1. These are the non-trivial zeros, and they encode detailed information about how prime numbers are distributed. Here's where it gets really beautiful, and honestly a little eerie. Riemann showed that you could write an exact formula for the number of primes less than any given value, and this formula involves a sum over all the non-trivial zeros of the zeta function. Each zero contributes a correction term, a wave, essentially, and when you add up all these waves, you get the exact prime counting function. The primes, those stubborn discrete objects scattered unpredictably along the number line, are somehow encoded in the zeros of a smooth function defined on the complex plane. The zeros are like hidden frequencies, and the distribution of primes is like a sound that's the sum of all those frequencies. It's a kind of Fourier analysis of the primes, which connects back to everything we were just talking about with Fourier series, and how you can decompose complex signals into simple waves. And Riemann noticed something about these non-trivial zeros. He computed a few of them, and they all had a real part equal to 1/2. They all sat on a single vertical line in the complex plane, the line where the real part of S equals 1/2. And he conjectured, he didn't prove, just conjectured, that all the non-trivial zeros lie on this line. This conjecture is the Riemann hypothesis. That's it. That's the statement. Every non-trivial zero of the Riemann zeta function has a real part equal to 1/2. It sounds almost innocuous, doesn't it? A claim about where certain points lie in the complex plane. But the implications are enormous. If the Riemann hypothesis is true, it means the prime numbers are distributed as regularly as they possibly can be, that the deviations from the smooth estimate given by the prime number theorem are as small as possible. If it's false, if there's even one zero off that critical line, it would mean there are unexpected irregularities in the distribution of primes, places where primes bunch up or thin out in ways we don't expect. Since 1859, an enormous amount of evidence has accumulated in favor of the hypothesis. Billions of non-trivial zeros have been computed, literally more than 10 trillion of them, and every single one sits on the critical line. Not one exception has ever been found. Hardy proved in 1914 that infinitely many zeros lie on the critical line, which was encouraging, but far from proving that all of them do. Various mathematicians have shown that at least a large proportion of zeros are on the line. Levinson showed at least a third in 1974. Conray improved that to at least 2/5 in 1989. But proving that every single zero, without exception, lies on that line, nobody has managed it. The Riemann hypothesis is one of the 7 Millennium Prize problems, each carrying a $1 million prize from the Clay Mathematics Institute. It's been open for over 160 years. Hilbert included it in his famous list of problems in 1900. When asked what he would do if he woke up after sleeping for 500 years, Hilbert reportedly said his first question would be whether the Riemann hypothesis had been proved. It's that central. And here's what's really worth sitting with as you lie there. This problem connects so many of the threads we've been following tonight. It connects infinite series to complex numbers to the distribution of primes. It shows how analysis, the mathematics of continuity and smoothness, reaches into number theory, the mathematics of discrete whole numbers, in ways that feel almost magical. The zeta function is defined by an infinite series. Its extension to the complex plane uses the same kind of analytic continuation that mathematicians developed while making calculus rigorous. The connection between its zeros and the primes uses ideas from Fourier analysis, and the question of whether the hypothesis is true or false bumps up against the foundational issues we talked about. Could it be independent of our axioms, the way the continuum hypothesis turned out to be? Most mathematicians don't think so, but the possibility has been raised. There's something fitting about ending here, with a question that's still open. Because if there's one thing I hope you've taken from everything we've wandered through tonight, it's that mathematics isn't a finished building. It's not a collection of facts carved in stone. It's a living, evolving, sometimes messy, sometimes breathtakingly beautiful human endeavor. People argued about negative numbers for centuries. The square root of -1 was dismissed as imaginary nonsense, and then it turned out to be essential for understanding electrical circuits, and quantum mechanics. Cantor was attacked for his work on infinity and died in a sanatorium, but his ideas became the foundation of modern set theory. Gödel showed that any sufficiently powerful mathematical system contains truths it cannot prove, and that discovery, far from destroying mathematics, gave birth to computer science. Weierstrass found a function that was continuous everywhere but differentiable nowhere, and instead of being a curiosity, it opened up entirely new fields. Every time mathematicians encountered something confusing, something that seemed paradoxical or wrong or impossible, and they sat with that confusion long enough, they found something deeper on the other side. That's the real pattern. Not that mathematics is confusing and then someone explains it and it becomes clear. It's that the confusion itself is a signal. It's pointing toward something your current framework can't handle. And if you follow it honestly, you end up building a better framework. And the new framework doesn't just resolve the old confusion, it reveals new landscapes you couldn't have imagined before. Negative numbers weren't just a fix for subtraction problems. They opened up algebra. Complex numbers weren't just a fix for certain equations. They opened up the whole complex plane, and with it, tools for understanding fluid dynamics and electromagnetism and quantum theory. Cantor's infinities weren't just a philosophical curiosity. They led to measure theory, which led to modern probability, which underlies everything from insurance to machine learning. And the Riemann hypothesis sits there, still unsolved, still beckoning, connecting all of these ideas in ways that Riemann himself could barely have imagined when he wrote those 8 pages in 1859. Maybe someone will prove it tomorrow. Maybe it will take another 100 years. Maybe, as some have speculated, it will require entirely new mathematical ideas that haven't been invented yet. Ideas that will seem confusing and strange at first, just like every other breakthrough we've talked about tonight. But you don't need to worry about that right now. Right now, you can just let all of these ideas settle, like sediment drifting slowly to the bottom of a still pond. The numbers, the infinities, the series, the primes, they'll all be there in the morning, unchanged, patient, waiting. Mathematics has been waiting for thousands of years. It can wait one more night. And you've done the hard part already. You've let yourself be curious. You've followed the thread. You've sat with the confusion instead of turning away from it. That's all mathematics ever asks. Just stay curious. Just keep following the thread. And for now, let that thread unspool gently into the dark and let the numbers carry you wherever you need to go.